test tool.
Finally, I want this.
So I will sit in the first row.
אישה אם אתה תרגיז אותי כמו לי כל הזמן, לא נוסע.
Okay, so we have the last part of the talks today. So Yishay Manzoor from Tel Aviv will be telling us about reinforcement learning.
Okay, thank you very much. So, my basic plan for today is basically to cover sort of classical material about Markov decision processes. Sort of, hopefully most of you sort of are not that familiar with the basics of a Markov decision process, otherwise I'm wasting my time and so are you. So here is sort of a quick outline of what I would like to do. I talk very shortly about the goal of reinforcement learning and then sort of dive into the mathematical model of Markov decision processes. I'm going to sort of introduce the basic problem of planning and learning, and then sort of hopefully we'll have time to talk about what we can do in an exponential size MDP, and I very much doubt that we'll have time to talk about POMDP. So let's see how much we can really cover out of this list. This should be more like a class lecture. If you have questions, ask. If we don't cover everything, it's a good sign.
Second lecture?
Both lectures. Okay. So reinforcement learning is somehow in the intersection of many fields. AI is probably sort of where machine learning is coming from, but it has many roots in control theory, in operation research. There are also like reinforcement learning in psychology and cognitive sciences. The reinforcement learning that I'm going to talk about is sort of related to the above three topics. It has this well solid foundation and sort of existed from the 50s, as you'll see as we'll go along. Typical applications. So the applications are sort of growing rapidly. This is sort of a list that combines old and new stuff. There's like, you can basically do control theory using reinforcement learning. There's a very nice project that was done in Stanford about helicopter control, robot soccer teams that were playing in a competition. There are also like the classical things are both new and old. Checkers is Samuelson from the 60s. Backgammon is Cesaro doing deep learning in the late 80s. And the new things are like a new Go algorithm and an Atari one. Those have received a lot of attention in the recent years. Pokemon not yet. Okay, and since the field sort of grew out of operation research, the classical things are really in inventory problems. So many of the motivations are really coming from scheduling and inventory problems. And the main reason and the main connection sort of to us is I think it's an important modeling tool about thinking about uncertainty. It gives you a basis of how to think on making decision when you are faced with an uncertainty. So the main difference is that what would be the objective? The objective would be sort of learning, but learning through interactions. So we'll be doing actions, and our actions are not only going to get rewards, like it was in Nicolo's talk, but in fact our actions are going to affect us. So we would like to do really control of a large-scale stochastic environment. But our knowledge is going to be partial, and this is sort of the uncertainty part that we have to cope with. So it's important to contrast this sort of with supervised learning or unsupervised learning. So in both of those cases, you are given the data and you're trying to do the best that you can with the data that you are given. As you'll see sort of when we talk, in reinforcement learning, what happens is that you're influencing what you are going to see. So for example, if I'm a robot and I'm looking straight ahead, I have no idea what's behind me. I may make perfect prediction about what I'm seeing in front of me, but this is not the goal, right? So in reinforcement learning, we will have sort of not only to do the best that we can given what we observe, but we also are controlling what we are observing. So here's sort of at a high level what we'll have. The system will have a state, and the algorithm will really influence the state. So if my state is, if I'm a robot and it's looking straight, this is what I'm seeing. If I'm turning my head, I'm seeing something else. So the algorithm influences the distribution. So this influences both the rewards and the observation. So therefore, this leads us to like an inherent trade-off, which exists also in multi-arm bandits, between the exploration and exploitation. Exploitation means that I'm doing the best that I can given the information that I saw. Exploration meaning that I'm trying things that I'm uncertain about, and maybe they would even give me higher rewards. So I have to balance the things, because if I don't explore, maybe I'm missing the terrific things that are there. And the mathematical models that we are going to use is Markov decision processes. So now let me, for a few minutes, define the model, and then sort of we can set up the basic problems in it. Okay, so Markov decision processes. The basic element is a finite set of states, a finite set of actions. We have some transition matrix, so it gives a probability given a state and an action, what is the next state, and there is a reward function, which given a state and an action would give us a reward. Being a computer scientist, you all know deterministic finite automata. This is basically the model. The only difference is that rather than seeing letters, we make actions, and we also get here the rewards. So picturally, this is sort of, we are in a certain state, we make an action. Given the action, we can continue sort of to a variety of state given the distribution, and this distribution is controlled by the transition matrix.
Yishai, so
Yes.
do we know which state we transition to? No, we don't, right?
We observe the state after we transition to.
But like, so we know, like, so there is.
Yes,
so
right.
Like in your like robot analogy, like I would say the state is like the state of everything around me. So if I like turn my head, I only like how does it?
So my state would be, would be maybe the angle of my eyes, right?
I see.
Right. Okay? And now what I observe is sort of an input that I'm getting. This is sort of the reward that I'm getting. Give me 5 minutes and then and then let's see if I can. Okay. Right. Okay. So now there is the transition part. The transition part is really defining the dynamics of how the things evolve. If I'm a robot and I'm taking my leg up and putting it down, this is how sort of my state changes. But then I'm getting also rewards from the environment. Basically, for a state and an action, I'm getting some reward. In general, it's going to be a random variable, but for simplicity, and in fact, in much of the literature, it's easier to think of it as the expectation of the random variables. So we'll just think of it as we are getting the expectation immediately. Just as you be aware, we can handle also random variable in a very smooth way, right? So here's sort of what a reward can be for a state in action.
And we know that expectation? Like this is also
now we're at the first part of the talk, yes. At the second part of the talk, we'll do learning, then no. And the third part would be an exponential size, and then it will be a double no. So we'll, okay, so right, but I think you got the answer, right? Right. So I try to be explicit when I do things. There is a process that gives rewards. We'll have to assume whether we know it or not. Okay. So what do we need to remember about an MDP? So when I'm running an MDP, how should I describe my history? So this is a way to sort of to think about the history. I'm in a state, doing an action, seeing a reward, and observing the next state. Then in the next state, I choose an action, get a reward, and observe the following state. And this is like a trajectory that runs inside the MDP. Of course, you can get to the same state more than once, and etc. Now, we are getting a sequence of rewards. And unfortunately, a sequence of rewards is something that's sort of very hard to optimize. So like most mathematicians, we would like sort of to collapse it into one number. And the question is sort of what is the right way of collapse? So before I'll sort of do the math of how we collapse it, I think it'll take me some time. So what are we aiming at, right? So first of all, we do aim that we would like to have rewards early rather than later. And then in some sense, sort of, we can differentiate between a system that is continuous, that never terminates, and a system that terminates. If you think about a game, it usually terminates. If you think about a robot or a system like this, it usually is continuous and does not terminate. And usually the return is sort of how we sum up all the rewards is going to be linear in the individual rewards. And here are sort of the three popular ways of doing it.
Sorry, I'm confused.
Yes.
So only the rewards come with a probability or also the state?
What?
Only the rewards come with a probability or even the states?
So when I'm in a state I'm doing an action, then I'm transitioning to a new state according to a certain probability distribution, and I'm getting a reward which can be a random variable, but for now let's think that it is deterministic. Okay? All right. We can sum up for a certain finite horizon, like a horizon H. We can do a discounting, which would be the most popular thing in reinforcement learning with some parameter gamma. Or we can take an undiscounted return. So here's the fun part. When you prepare slides, you're starting to think, okay, so for most of us in theory, we'll think about the finite horizon. But almost all the work in machine learning would be about the discounted. Why? So why would people that think about learning would prefer to think about the discounted return, not the finite horizon? Here's my answer.
They can die every day.
Think about how many parameters you need to learn, right? So here, okay, so maybe it's premature. So here, you will learn the number of parameters, which is a function of the number of states. But here, the number of parameters is like the number of states times the horizon. And the horizon could be fairly large. So from a learning perspective, it's much nicer to learn something which grows only with a number of states and not with a number of action, with the horizon itself. Okay. So what's our aim? Maximize the expected return. For the most part, I'm going to talk about fully observable. If at the end I have a few minutes, I'll talk about what is partially observable. And in a fully observable, we'll have a policy. A policy would be for every state to select an action. And basically, there is an optimal policy. So an optimal policy would be optimal for any start state. So from now on, I'm talking about only the discounted return setting. So there exists an optimal policy. It's going to be history independent. This you can see why, because we are in a Markov process and it doesn't make a difference how we got to a state as long as we are in that state. And it's going to be deterministic because you're not going to gain by mixing actions. You might as well just choose a single action. Okay, just to summarize the model, so we have a finite state of state, a finite state of action. We have a transition function, which is really stochastic. We have an immediate reward function. This is the reward that we get for each state in action. What we are looking for is a policy. It's a mapping from states to action. And what we like to maximize is the discounted cumulative return. So basically, returns which come far into the future are discounted by a factor of gamma. Yes?
You said on the previous slide that there exists history-independent policy, but
yes,
they are history-independent by definition, the way you define it.
Yeah, right, because okay. So I could have did a mapping from histories to action, you're right, and then prove that out of the class of histories to actions, there is always an optimal policy that takes only the last state.
What do you mean by you see the entire state?
You see the state. You see which state you're in. Okay. In a partially observable MDP, you see only a signal which is correlated to the state. Here you just know I'm in state 7. And state 7 is unique, yes?
One could imagine a setting in which one would get the, like in which the reward would be based on the state that one would go to?
Yes. Okay, so there are 3 ways to define the rewards. I choose state action. Some people choose only the current state, and some people do state action state. They're all equivalent. And it's a simple homework exercise that you are not going to get.
You need the set to be finite.
Yes.
So otherwise you don't have the norm.
When I get to POMDPs, I'll say something about it. Otherwise, I'm not going to have much. Or nothing, I'm not sure. Basically, the entire theory does need.
There is work on infinite state Markov to zero
Yes.
that
Right, but-
algorithmic work as well.
But you need to assume something. If you just say that it's infinite,
For example, arising from classes of automata theoretic models.
right, fine. Okay, so I'm going to do only finite. When I talk about the POMDP case, I'll mention an infinite one. Okay, this is what Nicolo did for me. This is a very simple case. Is
The slide or?
on the slide, but he did like a complete tutorial. If you think what is a multi-arm bandit, it's basically a single state. We are in a single state, so regardless of what we do, we stay in this state. And really the main thing is sort of how to choose the action. And there are various models that you can think about. If you can, I think this model was not mentioned so far. You can be stochastic like IID per action with a finite horizon. Kamesh described sort of the stochastic Markov process per action, discounted, and Nicolo did the adversarial setting. And this is sort of as much as I want to talk about multi-arm bandits. Now we can start talking about MDPs. So when I'm talking about planning, I'm thinking that I'm given a complete description of the MDPs. So I know I'm giving the transition matrix, and I'm giving the rewards. And basically what will be there's going to be 2 problems that I will be always thinking about. The first problem is, given a policy, estimate its return. The second problem is find the optimal policy. Somehow the first problem looks easier than the second, but later you'll see that they are intricately dependent with one another. So let's start with the first problem. Okay. So what do I want to compute? So really the intuitive value function is the first one. So I want that given a policy pi, define v pi of s, this is the expected return if I start from state s. Okay, this is really how much will we get if we run pi from state s. The second thing, this is a much less intuitive thing, but it's going to be critical for most of our understanding of MDP. It's called like a Q function, and it's doing the following strange experiment. It's saying I'm in state S. Regardless of what the policy wants to do, I'm going to do action A, and then follow the policy from that point on. Of course, if A was the action that the policy wanted to do, then Q of S, A, and V collapse to the same. But if it's different, then we'll get a different value. And what you'll see is that really this will guide us what is a better policy compared to our policy. Okay? When we talk about the optimal policy, we'll talk about it then with stars. So we have V star, Q star, and pi star. And what we'd like to have is that it's not clear a priori that there exists such a policy. So we'd like V star of S would be the maximum overall policy for this state. Okay. Okay, so let's start with policy evaluation. So now we can sort of write the equation of a policy. So what is the equation of a policy? So what is my return from a state S? So I'm taking a certain action, pi S. This is the return of this action. And now I got to a set S prime, which is sort of distributed according to the action that I took and the state that I was in. And from state S prime, I'm going to get this value, sort of by induction, or this is how I would like to think about it. So really what we have here is simply like a set of linear equation. If I write it explicitly down, I know the delta, I know the R, the unknowns are the V's, so I have a set of linear equations and I can solve it and basically for each state compute the value if I start from this state. Okay, here is a simple example just to make sure that everyone understands. So here is a very simple MDP. Here I put the rewards on the states, so I'll have less rewards. Let's take a discount factor of 1/2. And let's say I have 2 actions from each state. I can go either up or down. And my policy is a random policy. So if I write the equation, if I start from S0, with probability 1/2 I'll go to S1, probability 1/2 I'll go to S3. So I really need to average those 2. And my immediate reward is 0. So this is the equation that I get from state S0. And if I sort of write down the 4 equations and solve them, this would be the value function in each one of those states.
So Yishai, so here
Yes.
you assume that the transitions are deterministic.
No.
No, so how?
Oh, okay. In this example, no. Okay. Yes. Okay. In this example, given a state and an action, it's deterministic. Right. Yeah. Yeah. But it could.
Normally it doesn't have to be so.
Yeah. Right.
Sometimes even if I have a state and I choose an action, I have no control over which. I only know what is distribution. I have no control.
Right. No. Yes. Yes. Yeah. I should have made a more complex exam.
Yeah.
Okay. But I think it's clear. Sort of. It will just. I'll just have more terms here, right? But it's still a set of linear equations and equations. That's easy. Okay, optimal control. So to understand the optimal control, we need to understand really this function, the Q function. Okay, so the Q functions, if I want to compute it for a given policy, so my immediate reward is the reward that I'll get from S and A. And then I'm going to transition to some state S prime. And from that state, I'm going to use the value function. The value function of pi. So those things are already computed, so now I can easily compute these Q functions. And again, note that if I'm putting here the action that I really did with pi, this is just the value function for a deterministic policy. Okay. So here is a characterization of the optimal policy in an MDP. The policy is optimal if from any state the following holds. The value of the state is equal to the maximum over actions of the Q function of the state and the actions. Those are the Bellman equations. Why does this hold? So this slide has the easy part. Second slide, I'm less happy with it, but there's the other slide. Okay, so the easy part is assume there is a state and an action such that it doesn't hold. So it means that the value is strictly less than the Q value, right? See, it cannot be more, right? The value cannot be more than this because you chose one of the actions. Okay, so if it's strictly less, then okay, the first time that I get to S, well, I should do A because A is better and then keep pi. But then the next time that I get to S, well, the same logic applies. So I might as well just switch to A and basically get a better policy. Okay, so if V is less than Q, if we are suboptimal, but not only we are suboptimal, we know how to correct it. We need to switch to A. This is, okay, hopefully this will be partially understandable. But if not, I'm going to squeeze.
Shy, but formally it can influence other stuff.
Only positively.
Yeah.
Only positive. So it's important. So the way to think about it is you do it once, you already gained. Now you have this sort of weird policy that at S does A, and afterwards continues with pi. But the next time you get to there, you're comparing again the V of pi to the Q. So you're again gaining by switching. Okay. So for the other direction, what we need to say is that, okay, if this holds, this is the optimal policy. And the main issue is to show that the value function of the optimum is really unique. And the way the proof goes, and I'm going to go fairly briefly on this, is that we can define a nonlinear operator, which is really taking sort of the maximum over actions of a reward plus the transition. This is sort of the Q function if you think about it, right? This is the Q function, and this operator is sort of being greedy with respect to it. And what we need to show, in fact, I'm going to show it in a few more slides with a specific algorithm, that this operator is indeed shrinking. It's contracting. It will be contracting at the rate of gamma. Gamma is less than 1, so it will be contracting. So once you have a contracting operator, and you'll have a fixed point, and the fixed point will be your optimal policy, and the fixed point is going to be also unique. You can also show that the Q is going to therefore be unique. And because the V value is unique, there is only one V value for the that can solve it. There's only one solution to this, and therefore, if you got there, you have the optimal policy.
Sorry, what is TV, TV1?
T is an operator. V is the value function of S. Maybe I should put like parentheses here. All right. But this is not my notation. This is what they used. Okay. Okay. Here's a simple example of what an optimal control would be, right? We start with the same thing that we had before. And now what happens when we are in S0, we see that if we do +1, we get 5/6. If we do -1, we get 13/6. So basically what we can do, we can switch our policy to always from S0 to go to S3. And in this example, I think in one step, after you compute the Q functions, and if from each state you do the maximizer, you find the optimal policy. Okay. So now we want to compute the optimal policy. So here's 3 ways to do it. The first one is linear program. Most of you probably would be more comfortable to doing it, but let's do the other 2, because I think somehow no one really would use linear program to solve it. Because the 2 other methods are value iteration and policy iteration. What is value iteration doing? We almost saw it in the previous proof, right? What it does the following. It keeps track of a value function, and every time it has an iteration in which it maximizes over the actions, the immediate reward plus the expected future reward. And this is your new value function. And you keep iterating this until you converge or until you're close enough.
Do you do that for all
Yes.
stations?
Yes.
For all states simultaneously?
Yes. Yes. Yes, you're doing it for all states. Right.
But simultaneously or iteratively?
Yes, I'm not sure how. Yes. I think it will work even if you do it asynchronously.
Doesn't matter.
But let's do it. It will be easier for you to think that we do it together, but the convergence would hold even if we do it asynchronously. Okay. The other method is policy iteration method. Here we start with a policy, compute its Q function, and then given an action, okay, we are now greedy comparing with respect to the Q function and get the new policy out. Okay, so let me one slide for each one of those. Value iterations. Why do we converge? So let's look at the distance of the value functions from V star. Here I'm assuming that we are doing things synchronously. We are updating all the states. So we look at the difference between Vi and V star in norm L infinity. So what's the maximum difference that can be? So remember, this is like the Q functions. So let's see what's the difference between V star and Q of S and A star. This is Qi. So when I take this difference, the immediate reward will cancel out. And what I'll have here is the difference between the optimal thing, this is the V star, and this is sort of what I computed in the ith iteration. Okay? So this difference is bounded by, of course, so this is just something that sums up to 1. So this is bounded by the L infinity norm between V star and Vi times the gamma. Okay. But I'm not interested in this difference. I'm interested in the difference between V star and vi plus 1, but vi plus 1 is sort of just maximizing this. So it's basically, it's going to even be closer. So the difference between v star and vi plus 1 is going to be less than 2qi, and therefore, each iteration we are shrinking the L infinity distance by a factor of gamma, so the convergence rate will be something like 1 over 1 minus gamma. Again, polynomial not depending whether how you think about gamma. Are you thinking about it as a constant, or are you thinking about it as a parameter? Okay, value iteration, policy iteration. So what does policy iteration tells us to do? We compute the Q function given a policy. We take the best action from each state given the Q function. This defines a new policy, and then we reiterate. Right? So every time we compute the Q function, and we are greedy with respect to it.
Can you do this if you don't know delta?
If you don't know delta, I'll need to say how do you compute the Q function. In both, in the value iteration also, for now I'm assuming you know delta. Let's wait, not knowing delta, let's wait for the learning part, okay? Convergence, okay. So the nice thing is that the policies can only improve, right? Because when I'm greedy with respect to the Q, if you remember the proof there, what we said is that each time that you are greedy, you can just improve compared to the previous thing. So your value functions is sort of, for every state, you're doing at least as good as you did before. In fact, you can show that the number of iteration here is sort of, you can relate the number of iteration of value iteration and policy iteration, but notice that the iteration here are more expensive. Now the point is that unlike value iteration that doesn't stop at any point, policy iteration will stop because there is a finite number of policies. Each time we are getting a better policy, definitely eventually will stop. And the question is sort of when do we stop? So the confusing thing is that you can say that both polynomial and exponential and sort of in one slide. So it depends on the discount factor and how do we think about the discount factor. So if you think about an arbitrary discount factor, then you can show an example in which it's exponential. If you think about the discount factor as something which is constant, then you can show that it really converges in polynomial time. And I think in the workshop in like 4 weeks, Ye is going to give a talk, at least from the title of the talk, this is about this topic. Okay, so where are we? We talked about the blue stuff, right? So what I did so far, I defined the MDPs, and I talked about the case where we are given an MDP as an input, and we want to compute either the value of a policy or the optimal policy, yes.
So you heavily use, of course, that the gamma is less than 1, right? And,
no, it's discounting. It's right.
So you have the other objective also, the one that you take the average per step and you take the limit.
Okay, this is more tricky. You need, in order to, okay, there's literature there. In order to solve it, like you need to look at steady states, and you need usually to write a linear program to solve it.
So you also have like,
and there is. So there, sometimes you're not going to have an optimal policy, and you're not going to have values. Yes.
So is Strongly polynomial time algorithm known for the MDP stuff or not?
What?
Strongly polynomial.
So this one?
So any of these algorithms strongly polynomial?
No, so no, of course.
So I think that, okay, so it depends what do you call the discount factor. Do you count it as a parameter or not?
Right, so if the discount parameter is part of the input, then no strongly polynomial time algorithm.
Right. But if you say, I want 0.1, then the answer is yes. Okay, so now let's switch to learning algorithms. Sort of all of you are very much concerned, how do I know those models? So let me sort of, I'll describe two really learning algorithms. I'll do first the model-based, which is sort of the simpler one, and then I'll talk about the model-free setting. So again, for learning algorithms, we are still interested in the same two problems: evaluating a policy when I'm given one, and to find the optimal policy. And the two approaches, the model-based one, which is sometimes called also dynamic programming, for historical reasons, and for the model-free, I'm going to introduce something which is called the Q-learning. Okay, so let's start with sort of the model-based one approaches. So the model-based approaches is also right, is what you expect to do. You'll build a model, and given the model, when the model is accurate enough, you can solve it, given what I showed you in the first half hour, right? So you'd like to estimate the model from observation, both transition probabilities and rewards, and use the estimated model as the true model and find a policy. So the only thing that you'll need sort of to argue at the end, if I have an error in the model, they are not going to greatly influence my policy. So if I have a good estimated model, we should have a good estimation of the optimal policy. Okay, so we need to learn some policy run for long enough. We need somehow to define what is long enough, right? So during this time, right, we are doing only exploration. We just want to gather information about the model, and then we can build an observed model. But what is nice and simple here is that given a state and an action, the transition probably and the rewards are independent. So each time that I get to a state and do an action, I get another fresh sample of the transition probability and the reward. So really my main problem is to get enough of those. And if I get enough of those, I can build an observed model, and then on the observed model, learn an optimal policy. Okay. So let's first discuss the sample size sort of in a more abstract setting. So think about a simple abstract model. Then rather than needing to build a policy that will sample for us, someone gives us an oracle, and we can give the oracle a state and action, and it will sample from us the next state and the reward. And the question, how much time do we need to call this oracle? So first of all, we need sort of to test every state action. This is clear, but the question, how many times do we need to test it? So if you want an accurate model of the transitions, right, so from each state, you can transition to each other state. So you need a sample size which will grow something like the number of states times the log of number of state in action per state action. So this will give you a very good approximation of the transition matrix, and then any policy you will be able to approximate well from it. On the other hand, if you're just interested in the optimal policy, you can get around with much fewer samples. You just need a logarithmic number of samples per state in actions. And this is sufficient to approximate the optimal policy. It doesn't give you uniform convergence in the way that Eli sort of defined in the morning. It's not true that for every policy you'll get a good approximation, but if you're just interested in the optimal policy, it's good enough. One way of seeing how can you go from this sample size to this, you think about it that you're really just sampling those distributions enough times, and you are sort of have a very specific policy in mind that you'd like to evaluate, which is the optimal policy.
So,
yes?
you don't need to go over all actions?
So I'm saying this is per state action. This is per
log of the number of actions. So actually you don't try all actions.
No. Multiply this by S and by A. I'm saying per state action. Of course, you need information per state action. How much do I need to No, I'm for the other. How much per state action I need in order to gain enough information? There was another question. Yes?
Also for average cost optimization or only for discount?
What?
Only for discounted optimization or even average cost?
I think they did it for the discounted, but I wouldn't be surprised that you can do it. I'm not sure about the average cost. Okay, it's tricky to see the clock for me.
Yeah.
4 minutes. The clock is speaking. Okay. Let me let's finish the model based and then sort of take a break. Okay. So now So this oracle is like a clear cheating. This is, I think everyone has sort of noticed without me saying so. Okay. So what we'd like is to learn a model, and what we'll do is something. Okay. In reinforcement learning, there is like an on-policy algorithm and off-policy algorithm. On-policy is an algorithm that selects actions and performs them, and off-policy is sort of an algorithm that observes another policy that runs and tries to deduce from that policy various things. Okay. So now what we'll try to do is to learn it in an on-policy setting. Mainly, the learning would have control over the action, and its goal is really to learn a model. Later, he'll try to use this model in order to do. So as before, he would like to build an observed model, transition probability, and rewards. And the observed model would estimate the value. Given the observed model, we can estimate the value of the policy. Okay. So what is our real problem, right? So in the oracle, we can just give any state and any action and get the reply. But we somehow need to reach new places here, right? We need to reach states that we have no idea how to reach. And here's sort of a neat idea how to do it. Split the state space into two parts. The green part are things that are already very well sampled. You're fairly certain about their transition probability and their rewards. And the red part, you either have no knowledge or very few knowledge. You would like to get more information in this part. Okay? So how can we sort of go from the green part to the red part? Question. Okay. As a hint, you already saw it. Okay. This is a planning problem, right? So think that this is really the high reward states. Right? This is nothing to do with the real rewards. This is like imaginary high reward states. Those are low rewards. And really, the exploration is just doing a planning in the new MDP. So in the new MDP, if I do a planning, it will guide me from the green states as short as I can to the red states. So this would give me sort of a way to sample in a fairly fast way. And I think let's take a break here and then questions before we take a break. Great. Okay, one question. Oh, so if I get to a high reward state, okay, what did I do? Think of collapsing all this to a single state, and any action stays in the state. So I want to force my optimal policy to get to this state as fast as possible.
So is this better than doing just random actions for some time?
Well, if you do random actions, you might get stuck somewhere here. And you never would, might take you exponential amount of time to escape and get here, right? So think there's like a long line with the very specific actions that you needed to do in order to get out of it. So here you sort of you're building the prefixes one after the other. Here, so here, okay, so now I need to remember. I think it takes something like n cubed. You can show here. It's going to be polynomial. This is definitely. Okay, let's.
So now we have a break. We'll meet back in half an hour.
Okay, great.